So just believe me that you get t minus 1n if you go around n times, if you start looping around in the center n times. So here we looped around twice. Just count 2 blues up there. So we got, we looped around once, I'm sorry. Because this one's the loop right here. You know, this one we just have to do. Doesn't count. But we did one extra loop. So we got t to the 1, which is t to the 1. The first time we did 0 loops, so we got t to the 0, which is 1. In general, if you do extra loops, you're going to get t to the 1 minus n. All these are different paths. You have to sum up over all of them. You have to, because that's the way you compute Lenz's thing. You have to find out the final likelihood from getting from 1 to 1. So you have to do this infinite sum. It's a geometric series. You get 1 over 2 minus t. And in general, you're going to have to do infinite sums for the other ones too. Because there's many paths you can take. Notice this one. This is one possible predictor, right? I don't count this as looping around because I never repeated kind of a path, see? I never repeated a path. You can think of me as going higher and higher in a highway. But here, I jumped back down on the previous path. So I consider that looping once. And you can imagine I could loop twice, or 3 times, or 4 times, or 5 times, and all of those are distinct paths I could take, from starting from one ending at one. I have to sum up the weights of all of them, because they all contribute. So in that case, I sum it up, I get 1 over 2 minus t. It's geometric sum, geometric series. And you have to do that for all of them, really. I don't think there was one in this case where you don't have to, but I could be wrong. So in general, you have to do infinite series. Lin showed that all the edges of these matrices converge, which is important because for Borel, you don't have to worry about that, even if you use the probabilistic thing. You can't loop in Borel if you use this jumping off thing, this jumping off story. He also showed that the representations respect, the representation rule that A times B equals C implies matrix of A times matrix of B equals matrix of C. He also created this other method which can avoid doing these infinite sums if you really want to, which uses just linear algebra, which is actually kind of cool and is useful when things get too complicated, but it's cumbersome when things are kind of simple. Like that one, I would not really use that method. And lastly, he didn't do this, but we figured out that you can extend this just as easily to some tangles, not all of them. Some very simple tangles. Ones that start with the same number of points end with the same number of points. So, and that's actually kind of useful for something much later that we do. So now the skein representation. Different representation, kind of switching topics here, because we studied 2 representations, one the skein. The skein representation is defined in terms of 2 other representations. This is scalar representation because it's just a multiple of, well, it's the scaling of graph. I guess it's not clear, but basically this is the ith generator of a braid. That is, again, the same ith generator, and we apply the Borel onto the ith generator. For every ith generator, for every generator we have, you pick up a negative t to the negative 1/2 power. Why? It's important later. Why it's that particular value. And so, if you have if something is made up of 3 generators, 3 positive exponent generators, you're going to pick up negative t to the negative 1/2 3 times. Every time you have a generator, you pick up the scaling factor. And if you have inverse generators, it's now negative t to the 1/2 power. The scalar representation is simpler. It says if you have a generator, just replace it with negative t to the 1/2, negative power. And for inverse generators, it becomes negative t to the 1/2 power. So it's very simple. That's why it's called the scalar representation. So you just turn it into polynomials, really. So if something is made up of 10 positive, if something is made up of 9 positive exponent generators and 2 inverses, you're going to have 9 of these. This to the 9th power times negative t to the positive 1/2 to the 2nd power. It basically counts up your positive generators and negative generators. It's a very simplistic representation. On their own, they're not very useful. The skein representation, though, should work for string links. So how is it that I can define my skein representation with this, which is really the definition? You need something to break it down into braids. So basically, just as a point out, you're taking the matrix of the Borel, scale of Borel, which gives you matrices, and dividing by polynomials. But we need to break it down for this to work. So, this wasn't supposed to be here. But, okay. But I guess I could point this out anyways at this stage. Notice that if L was a braid, you're going to get the same answer. as the Borel representation. You need to do a little work. It's not obvious, but it doesn't take many lines to show that if you apply psi first to a braid and then apply the epsilon to a braid, all your t's are going to cancel, top and bottom. It's not too hard to believe, because every time you get, let's say you have 3 positive generators, you pick up 3 negative 2 to the negative 1/2. Epsilon is also going to have 3 positive generators, so you're going to pick up exactly negative 2 to the negative 1/2 3 times. All those t's are going to cancel, top and bottom, and you're just left with the Borel representation. Because if you recall, the psi gives you Borel. So all the t's cancel, all the scaling factors cancel, and you're just left with a Borel matrix. So before I show you how we can decompose it into string links, I should point out a few things. The scalar representation is generalizable to tangles, all tangles. In fact, it's not generalizable. That's actually how it's originally defined. My advisor wanted to define a representation on tangles in general, which is actually a weird idea to explain. But he wanted to do that, and so they did that for his PhD or master's thesis. And so it works more in general, but it's too complicated to define in general. For string links, it's simpler. It's composed of 2 representations which are going to be compatible with Conway's skein relation, which I'll show on the next slide. And it also generalizes the Borel representations I showed in the previous section. So it respects the Borel representation, but it also is well defined in the sense that if they're equivalent, they're going to give the same matrix. This is very important. Otherwise, it's not truly a representation of what we're talking about. So here's the skein relation that I've been mentioning. So what it does is, imagine you actually have some string link, right, ambient, out here. We're focusing on one crossing now. That string link, we're going to say, and just work with me, we're going to say that is going to equal z times the string length with that crossing replaced with the smoothed out version. So you have stuff going around here, but we're looking at one section. And if it was like this, we're going to say, now it's like this. We're just going to change it and say this equals z times that guy, plus that same string length, but instead of this, it's now this. Switch. This is how it goes for positive crossings, this is how it goes for negative crossings. And you can probably convince yourself really quickly that to get this one, you just solve this one for a negative crossing. That's all I do. So really you only need one skein relation. And z is this guy. He's t to the 1/2 and t to the 1/2. So this is, now you might sort of see hints why we chose t to the 1/2, t to the negative 1/2. Something, they're related somehow. They are. So when we resolve, now we can resolve string links. We can apply the skein relation progressively. And the skein relation, by the way, comes from knot theory, and it was used to find knot invariance. Here, I guess we're using it to find string link invariance. You focus on a crossing, that one, which is positive. You get z times that guy. Notice how it was smoothed out, right? Plus that guy, the original guy, crossing switched. They can be simplified. You get that and that. They're quite simple and simplified, which is useful to see. But now that one is the inverse generator, and that one is just the identity. So really we can just write it as e times the inverse generator plus 1, which is the very bottom. Hard to see. Sorry. So that's what we do. We resolved it all the way down to a linear combination of braids. So let me, before I go on. So now that we've resolved it all the way down to a linear combination of braids, now we can apply the psi and the epsilon. What happens is I apply psi to this, to what I have here, right? Psi distributes over addition because we define it that way. So it's going to be z times psi of this guy plus z times psi of this guy. And that's going to be what psi spits out. You're going to be adding matrices and multiplying by z's. Epsilon is going to be z times, which will be, I think, 2, negative 2 to 1/2 plus 1, which will be shown on the next slide. So you get the sum of matrices on the top, and you get this polynomial on the bottom, and you have to divide. That's how you compute the skein representation. It's a bit weird, and it seems like it came out of left field or out of some swamp, but what's going to happen is interesting. So let's actually work it out. So remember, it was z times sigma inverse, so we get our negative 2 to 1/2 plus 1, like I said. Z was this complicated thing. This 2 to 1/2, negative 2 to negative 1/2. Multiply it out, you get 2 minus t. Psi, I don't expect you to do this all on your head. But if you can, then you'll see that it boils down to that thing called Bob. So finally we get this. This might look familiar, and it is. It's the same exact thing. These two things are defined very differently. Very, very differently. And they yielded the same thing for this, and this was the seed for this project. Is there other examples? Can there be more of these string links which agree? Does it agree for all? There's counterexamples, things like that. So it's not a one. There's actually more examples. This is an example of something that's not a string link, which it also works on. Skein, remember, works on general tangles. It also works on that. Lin, like I said, we can extend to tangle-like things. Not technically all tangles, but some of them. It will agree on all of these. The three-stranded fish, this guy, that guy, and there's other examples. The three simple examples. And I should point out that if I square this guy, like this guy times this guy, it also works on that. If I take any things for which it works, for which it agrees on, both skein and lin, if S and L agree on some particular set of string links, if I multiply them however I want, it will also work on any product of them. Because that's the property of representation that preserves multiplication. So if it works for two of them, if I multiply them together, it works for this new one. So really, I can take this to the nth power and it's going to work. So really, anytime I find one that for which it works for infinitely many. And every time I add a new one, you get all these products for which it works. But these are, irreducible, like prime, I guess you can think, and it works on these primes. It also works on this twisty family. Why this one's interesting is because it's not finally generated. You can't take any two guys in this family, multiply them together, and get another one. Notice what I did. I twisted twice every step of the way. All these guys are. So what I've done is, in the previous slide, I mentioned that if I take any things for which it works and multiply them together, I can get more things for which it works. And then I have a set of primes which give me the ones it works on. But now, because of this, I have infinitely many primes for which it works. But that's not all the prime string links, the ones that are irreducible. There's many more irreducibles possible for which it works. Or maybe there's not, but I don't think that's the case. And so that's the key point about this family that's nice because they're not finitely generated. They're infinite algebraic in an algebraic sense.
You multiply the second one, and multiply the second one.
The second one?
Yeah.
It will just stack it on itself. So you get a twist in the middle, and then it gets great.
It's not going to be yeah.
So it's kind of weird. Yeah. And furthermore, here's another thing that I proved. There's this huge family for which it works that is also not finally generated and seems much more varied. If you have string links for which the strands do not interact with each other, notice that the first strand and second strand don't overlap, don't intertwine, don't interlock. Completely independent. I could draw a line and separate them if I wanted to. If you have this independence of strands, then they just go to the identity matrix. This will be when I do either skein or lin, I get 1, 0, 0, 1 for this one. And if I had 10 strands, which did crazy things, nodding with themselves and stuff, but never nodding with each other, that would go to the n by n, or the 10 by 10 identity matrix. So because each of them go to the identity matrix, I have essentially proven that they agree on these humongous family of things. Because basically every knot can be turned into a strand. Just cut the knot open and turn it into a strand. So for every single knot I have a string link for which it works. So it's a big family. This can pretty easily be extended so that I also get my string-like tangles where I have loops. It works there too. Now the restriction is the free loops can't interact with more than one strand at a time. Loops can interact with loops, but you can't have loops interact with two sides. There can't be any interaction between the strands, even through loops. And this will also go to the identity matrix. So it's even, the family's still infinite. It's still not finitely generated, but it's a little bigger now. So unfortunately though, I couldn't find a general proof. So for this working in all cases, not even in the case for 2, which I started trying to do. So instead I said, okay, forget this. I'm going to just see what happens if it was true, because apparently I'm not smart enough to figure out if it is true or not. So I say, let's assume it's true for the case of n equals 2. And